The ratio test. Let the sum from n equals 1 to infinity of a sub n be a series of non-zero terms. Number 1. The sum from n equals 1 to infinity of a sub n converges if the limit, as n approaches infinity, of a sub n plus 1 over a sub n, absolute value of that, is less than 1. 2. The sum of a sub n as n equals 1 to infinity diverges if the limit of, as n approaches infinity, of a sub n plus 1 over a sub n, absolute value of that, is greater than 1. The ratio test is inconclusive if the limit is equal to 1. So let's take some series. How about 1/2 plus 1/4 plus 1/8 plus 1/16? Now if you take any two of those, let's say the nth term and the n plus 1 term, and you divide them, a sub n plus 1 over a sub n, we have 1/4 over 1/2. And if you multiply the top and bottom by 4, you get 1/2. Now that's less than 1, and really what you're saying is you're adding less and less and less and less. If it was the other way around, if the series was adding more and more, 1/2 over 1/4 is 2. So that's greater than 1. You're adding more and more, not less and less, so the series won't be converging at all. Series involving factorials and exponential functions work especially well with the ratio test. Example 1. We have 2 to the n over n factorial. The ratio test says take the limit as n approaches infinity of the absolute value of 2 to the n plus 1 over n plus 1 factorial. That's the a sub n plus 1 over a sub n. So we have over 2 to the n over n factorial, and the absolute value of all of that. Instead of dividing, let's multiply by the reciprocal. So here's the big fraction right here. Instead of dividing, we're going to multiply by the reciprocal. We have 2 to the n plus 1 over n plus 1 factorial, and then times n factorial over 2 to the n. Let's take care of the 2's first. We have 2 to the n down here, and we have 2 to the n plus 1. So we have an extra 2 on top. Now we have the limit as n approaches infinity of the absolute value of 2. We can write n plus 1 factorial as n factorial times n plus 1. And when we do that, the n factorials will cancel out, which leaves n plus 1 in the denominator. So we have over n plus 1. Now, when we plug infinity in for n here, the denominator gets very big, and this goes to 0. That is less than 1, so this series converges by the ratio test. Example 2. We have n squared times 3 to the n plus 1 over 2n. We'll do the ratio test on this. Limit as n approaches infinity of, we have a sub n plus 1, which will be n plus 1 squared, times 3 to the n plus 2, over 2 to the n plus 1. Now instead of dividing by a sub n, let's multiply by the reciprocal. We have 2 to the n over n squared, 3 to the n plus 1. Let's take care of the 3's first. There's n and plus 2 here, and there's 3 to the n plus 1, so there's an extra 3 on top. We have the limit as n approaches infinity of the absolute value of, we have an extra 3 on top. How about the 2 to the n plus 1 and 2 to the n? There's an extra 2 in the denominator, so that puts a 2 down here. And with the n plus 1 squared over n squared, there's not much we can do. We have n plus 1 squared over n squared. If we multiplied this out right here, we'd have n squared plus 2n plus 1. And then now this is a rational function. So now we can just use our rational function rules. When n approaches infinity, the ending behavior of this function, and the ending behavior is 3/2, which is greater than 1. So this series diverges by ratio test. Example 3. We have n plus 1 at factorial over 3 to the n. We have the limit as n approaches infinity of the absolute value of n plus 2 factorial over 3 to the n plus 1. And then instead of dividing, let's multiply by the reciprocal. We have 3 to the n over n plus 1 factorial. That's equal to the limit as n approaches infinity of the absolute value of, this can be written as n plus 1 factorial times n plus 2. So the n plus 1s will, n plus 1 factorials will cancel out, and we're left with n plus 2, not 3. Let's get rid of that. We have n plus 2. So that takes care of all of those, and now with the 3's, we have an extra 3 in the denominator. So this is equal to infinity, which is greater than 1. So this series diverges by the ratio test.